Hello, in this video we're going to go over the squeeze theorem for limits. I'm just going to go over the theorem in this one, and then there'll be a couple videos where we just have some examples. I think the easiest way to explain the squeeze theorem is just to take a look at a graph, and then we'll write down the formal theorem. And then again, in the next couple videos, you can look at some examples. Okay, so I have a graph here. I'm going to call this function h of x. I'm going to add another function now. I'm going to call this bottom function g of x. And then I'm going to add a function in the middle. And I'm going to call this third function f of x. All right, now let's just take a look at what's happening here. We have this x value right here, which is 1. And that h of x and g of x meet at 1. Right? When x equals 1, they meet, and that looks like a y value of 2. So you have the limit of h of x as x approaches 1 is 2, and you have the limit of g of x as x approaches 1, also 2. But let's talk about the properties of f of x. What you notice is that g of x always smaller than f of x, or that's always smaller than h of x. So you have this middle function f. It's smaller than h, it's bigger than g. But notice that at x equals 1, they all meet, right? If this f of x is always between the two functions and they're going to meet at this point, then what does the limit of f of x have to equal? Just common sense. I mean, you're looking at the graph. You should see it even without looking at the graph. But common sense is that the limit of f of x also has to equal 2 because of this property, right? F of x is always between g and h, actually near x equals 1. That's really what we care about, is that in this region, that if f is going to stay between the two functions, then if they all meet at that spot, then they all have to have the same limit. Okay, just to even if you haven't been convinced yet, I'm going to zoom in and I want to take a look at what it looks like when I'm closer to this point. Okay, that's zoomed in a little bit. You can actually see that f of x is still staying between h and g. Zoom in a little bit more. Okay, I'm pretty close now. There's h, here's g, and then again here's f. So again, as long as f stays between h and g meet at a specific x value, then f also has to have that same limit. So let's go ahead and write down the formal theorem. So suppose you have three functions. You have g of x less than f of x less than h of x when x is near a, which is kind of what's happening here. You got h and g. The except possibly at a means that I could have actually had an open dot and a specific value for f somewhere else. But again, remember, limits don't care about specific y values at a. And you have the property that the limit of g equals the limit of h. So this would have been L, right there. So you have this property, and finally, you have this conclusion. Because f stays between g and f, that means f, the limit of f has to stay between the limit of g and h. So you can have this conclusion that the limit of f is also L. Now, why is this important? This function right here that for f is a very complicated function. All right, h and g are supposed to be nice and easy. You can actually see they look like parabolas, nice and easy. But f, very complicated. So if you can figure out two nice functions, h and g, that have the property that f is always between it, even though it's very complicated, as long as it's between h and g, and you know the limit of h and g, then it forces f of x to have the same limit. So that's why the squeeze theorem is good. We're going to go ahead now and do some examples.